Hello, physical science students. Let's go over the study guide and review for your interim for tomorrow. I am going to go over the answers to these problems, and hopefully this will get you a little bit more prepared and feeling a little more relaxed. Okay, here we go. Let's go through number one. This goes back to balanced and unbalanced forces in ticker tape models. It says, the ticker tape diagrams for 4 different moving objects are shown below. Circle the ticker tape diagram that show the motion of an object that has been acted upon by a net unbalanced force. Use the number next to the diagram. Well, that's just for decoding. We're not going to worry about that. All right, this is where the problem kind of stops. So let's remember that whenever we have a net force, that is always going to equal motion, because right, it's a push or a pull. If there's a net force acting on an object, then that means that the object is going to accelerate as long as that force is acting upon it. So if we see net forces, we know acceleration is happening. And conversely, if there is no net force acting on an object, then there is no acceleration, meaning the object is either going to remain at rest or in motion at a constant speed. Right? This is Newton's first law of motion. So let's look at these. In the first one, we can look at the distances between the dots. And if I look at the distances, now remember that speed is equal to distance divided by time. If I look at the distance, each one of these has the same distance. And we already know the drop, that if we were imagining these, for example, as oil drops out of a car or a leaking bag of water, that right, they're dropping at a constant rate. So the time is always the same between the dots, but sometimes the distance changes. In these, every distance is the same. That means the speed is the same between every set of dots. I know that this one has not been acted upon by a net force. It's just moving in constant motion. Look at the one underneath it. The distance between these two dots is different than the distance between these two dots and these two, and etc. I notice that this has an increasing distance, right? The distance divided by time of these dots is much greater than the distance divided by time of these dots. This means not only does this have a positive acceleration, in order for that acceleration to happen, it must be being acted upon by an outside force. Let's go over to this one. If I look at the distance between each dots all the way across, they are the same. The same distance divided by the same time means the speed stays the same. This is not being acted upon by an outside force. In this one, I notice that my distance divided by time, each time, my distance is smaller. Right? My distance is getting less and less. That means my speed is decreasing. This is negative acceleration. Okay, that means it is being acted upon by an outside force to reduce its speed. So these two were our ones. So if we ever see the ticker tapes changing in their distances, that tells us the speed is therefore changing. Right? If we look at a velocity time graph, this one would look like this. And if we looked at a velocity over time graph for this one, our velocity would be decreasing. All right, let's look at number 2. This one is actually a two-parter. An object acted upon by 3 horizontal forces experiences an acceleration. And it says solve for the mass. And it says it's acted on by some forces. So I know this goes back to my friend force equals mass times acceleration. Well, I don't know what my mass is. That's what I'm trying to find. My acceleration is 2, so I need to figure out what my applied force is. What is the actual force that's being applied to this? Well, in this case, I've got 100 newtons and 10 newtons in this direction for 110 newtons to the right, and I have 30 newtons in the opposite direction, counter to these, meaning they're going to be canceling out some of the force that this side is pulling with, So we're going to subtract those newtons, and we're going to end up with 80 newtons to the right. So we're going to take that 80 newtons, we're going to put that in for here, and we're going to 80 equals m times 2. To get that m by itself, we're going to divide by 2, because 2 divided by 2 is 1. And then whatever we do to one side, we do to the other. And so my mass is 40 kilograms. In this one, this is still applying force equals mass times acceleration. It says circle the objects that are accelerating. Remember that for something to be accelerating, it must have a net force acting on it. Something has to be pushing it or pulling it to change its speed. So in this case, 25 newtons to the left minus 25 newtons to the right, 0 newtons. This one is not being acted upon by an outside force, by a net force. Net meaning, right, in total. It's going to either stay still or keep moving at the speed it already is. In this case, I've got 15 newtons to the left, 25 newtons to the right. These are going in opposite directions. We're going to subtract them. So 25 minus 15 is 10. I have 10 newtons to the right. Now my object is going to be accelerating, and it's actually going to be accelerating in the right direction, towards the right. Okay. For the last one, like the first one, I got 25 and 25 newtons acting, but the forces are in the same direction. All right, so this is like you're pushing a heavy box. Somebody at the front is pulling it, while somebody behind is pushing it as well. And in this case, they're going to combine, they're going to add together. So we have 25 newtons plus 25 newtons. We have 50 newtons to the right. So in this case, which one's going to be accelerating faster? If their mass is the same. If their mass is the same, and these are the forces being applied, this one is obviously going to accelerate more. All right, let's go on to number 4. Number 4 is still a force equals mass times acceleration. We've got a 14 kilogram, that's the mass. It says it accelerates, so we know we're talking about acceleration. And it says calculate the net force, so we have a force. Well, and it does give us a hint. I know I have force equals mass times acceleration. In this case, I know my mass. I don't know my force. That's what it wants me to find, which means I have to use other tools to figure out the acceleration. Now, if you remember back from 1, I showed the velocity time graph. It happens to be that in velocity time graphs, if the line is linear, in this case, slope, the value of the slope is equal to the quantity of acceleration, how much acceleration is happening, right? Our slope equals our acceleration. So just like in math, we find our change of y over our change of x to get the slope of a linear equation. Same thing here. Our change in velocity, which is our y, divided by our change in time. So let's figure this out. Now there's a couple places we can stop. I'm actually just going to go from here all the way to the end because the math will be the same. I know that my velocity went from, the story this tells is that my velocity went from 0 to 6 meters per second. So my change in velocity was 6. And the story this graph tells me also is that it went those 6 meters per second. It took it 4 seconds to reach that velocity. And I'm going to divide those two. So 6 divided by 4 is 1.5 meters per second squared. And so I'm going to put that in here for my acceleration, and my force through the power of the calculator is 21 newtons of force. That means to get a 14 kilogram object accelerating at 1.5 meters per second, you must be pushing on it with a 21 newton net force. The velocity of an object over a 5-second period is shown in the table below. Calculate the acceleration. Well, remember that this is the same as like an XY table. Now, this is an XY table that's represented in a graph form. Same thing here. It's the same change in your Y over your change in your X gives you your slope, or your rate of change. Same thing here. Change of velocity over change in time. Now I can use I'm going to use my first times, but I can use any value in here. I'm going to go to the end to find out my overall. So I'm going to go my change in velocity through over 5 seconds, because it says a 5-second time period. It went 20 meters per second. It accelerated up to going 20 meters per second in 5 seconds. And in this case, so we're going to divide that. It is 4 meters per second squared. I can also check that to see, for each 1 second that this goes up, does my velocity go up by 4? Yeah, it does. Number 6. Determine which of the following objects has the greatest momentum. All right, so we are dealing with our friend momentum now. Our momentum is our inertia it's our inertia in motion. It is how hard would it be to stop this object. Momentum is equal to mass times velocity. So in this case, we have a mass, we have a velocity. The momentum in this is 16 times 2. In this problem, momentum is 1 times 20, and in this one, it is 100 times 0. Which of these has the largest momentum? This has a momentum of 32. This has a momentum of 20 kilogram meters per second. And this one has a momentum of 0. This one is important to note. It doesn't matter how large something is, how much mass it has. If it is not moving, it does not have momentum. Momentum is inertia in motion. Something must be in motion in order for it to have momentum. All right. Number 7, use the diagram below to determine the unknown momentum after the collision. So we have two objects that are moving towards each other. This one is moving to the right, this one's moving to the left, and afterwards they are going to be, we know that this one then starts moving to the left at 12 kilogram meters per second. We don't know the momentum with which this one is moving. However, we know through the conservation of momentum that these are equal, right? What happens, the momentum that exists in the beginning in the system is the same amount of momentum at the end. It just gets redistributed. So 56 plus, because my momentum of object 1 plus my momentum of object 2. Now object 2 is 2, but with momentum, the direction matters. When it's going to the right, it has a positive momentum. When something is moving to the left, we give it a negative momentum. So this is 56 plus negative 2 equals 12 kilograms. Now notice that is to the left, so that's negative, plus unknown. I'm going to put mass 2 because we don't know what that is. All right, I'm going to combine my values where I can. So I have 56 plus negative 2 is 54 equals negative 12 plus m2. I need to get my variable by itself. So right now I have negative 2 being added to that. So I'm going to add a positive 12 to this side to cancel that out. Whatever I do to one side, I'm going to do to the other. So I'm going to have 66 equals my momentum of my second object. So my second object is traveling much farther to right, 66 meters per second squared. Again, if you think about it, this one had 56 kilograms of momentum going to the right. but after it stops and starts moving to left at quite a good amount, at quite a good click, right? So that's that. This one didn't have a lot of momentum, but it got hit pretty hard by this, and so it hits and it's going off in the opposite direction. Okay. We're going to come back to number 8 at the end. Number 9, a 5 kilogram object on Earth has 4,753 joules of gravitational potential energy. Calculate the height of the object with respect to the surface of the Earth. Now this is the energy one. This is the stuff we've done most recently. Gravitational potential energy. Sometimes it's written like this. In some things we've seen it written like this. Either or. Okay, same thing. Is equal to, their gravitational potential energy is equal to the mass of an object times the acceleration due to gravity here on Earth times the height of the object. So we know that it has this much energy. We know that it is 5 kilograms. We know that the acceleration due to gravity is 9.8 here on Earth. But what we don't know is how high the object was lifted up to have that much energy. Oh, we can calculate that. All right, let's go ahead and magic a calculator. I have 49. 5 times 9.8 is 49 times H, 53 joules. Is it a pain in the neck to rewrite this each time? Sure it is. Does it help us keep our information organized so that we can clearly do the next step? Yes. So I need H by itself. So I have 49 times H. I'm going to divide by 49 to get H by itself, because 49 divided by 49 is 1. And whatever I do to one side, I do to the other, and that is going to give me my answer. So I'm going to do 4,753 divided by 49, and that is going to give me 97. So my height is equal to 97 meters. Meters is my unit. All right, let's go on to number 10. A 4 kilogram object has 98 joules of kinetic energy. Calculate the velocity. All right, I need my velocity. I have a mass. I have an energy. And it's kinetic energy. My kinetic energy equation is 0.5. So half of the mass times the velocity squared. So here we go. I have 98. So that's a 0.5 times 4 times velocity squared. 0.5 times 4. 98 equals 2 times velocity squared. I'm going to rewrite it over here. I need to get velocity squared by itself, so I'm going to divide by 2. Divide by 2. 98 divided by 2 equals 49. Velocity squared. Now, that's not velocity by itself, it's squared. That doesn't mean v times 2. That means squared, so we have to use the square root operation. Remember, square root on a calculator is second x squared, right, to give us that, to get that little square root that's above the mark. I can just type in 49. It is 7. That means that our velocity is equal to 7 meters per second. All right. A small object is released from the top of a ramp. Before release, the object has 214 joules of gravitational potential energy. At some point along the path, it has a gravitational potential energy of 128. Assuming no friction, what is the kinetic energy of the object at that point? This is a conservation of energy problem. We know that the amount of energy at the start of an interaction is going to be the same amount of energy at the end, as long as no energy has left the system for things like friction, but there's no friction here. So it says it started from rest at the top of the ramp. That means that its kinetic energy is 0 to start. It tells us that its gravitational potential energy is 214 joules. Now, that means the total energy of the system. Our total energy is equal to our kinetic energy plus our gravitational potential energy. So in this case, our total energy is 214 joules. That means, because we're not losing anything to friction, anywhere on here, even right as we reach the bottom, it is going to still have a total of 214 joules. So let's say it's rolled down to about this point. Well, it has a gravitational potential energy. It's actually going to roll down, I know, less than half, because it's less than half. Let's say it's about there. At this point, its total energy is still 214. Right? Between the potential and kinetic, it's still 214. Its gravitational potential energy has dropped to 128 joules because some of the gravitational potential energy is now kinetic energy. The ball is in motion. In fact, it's in increasing motion. It's increasing speed all the way down. So, define my kinetic energy. Total minus the part is going to give me the missing part. I'm going to do 214 minus 128. 214 minus 128. That tells me that at this point down the ramp, it has accumulated 86 joules of kinetic energy. Now, where could I go from this? If I know the mass of the object, I can figure out how fast the object is going, which is kind of pretty cool. All right, an object, let's go to the last one. Now the last one says an object slides down a ramp as shown in the diagram. How much energy is lost? In this case, it's losing it to the surroundings. The type of energy that gets lost when friction happens is thermal energy. Where does the thermal energy go? It goes into the atmosphere. Some of the energy, as it's sliding, the friction will add heat to the ramp. Some of it will even go into the object itself. So some of the potential kinetic energy is just going to change form. It's not going to disappear. It's not going to be destroyed. It's going to change into another form that's no longer part of the system. So total energy, our starting point is, our total energy is going to be these two together. It is 1,280 joules. Now, if there were no friction, this would also equal to 1,280 joules, but that will not be the case because some of it has gone away. So over here, our total energy is 1,236 joules. Okay. I have this many joules. I only have this many left. Some of it disappeared. How much disappeared? Well, we're going to use subtraction. Right? We're going to subtract our two total energies to figure out what happened. Where did it go? So, 1,280 minus 236. Oops. 1,280 minus 1,236. Now, I knew I made a mistake when I saw I had such a big answer because I know I'm taking almost all of the energy away. I know I should have a very small answer. 44. I have 44 joules of energy that have left because of friction and have become thermal energy. And out into the atmosphere it goes. Let's go back and finish number 8. Number 8 is the most challenging of the problems. Okay, let's check out our last problem. I know that my momentum plus my other momentum is going to be equal to my momentums after. Now, before the explosion, these both have, in an explosion, this one's a little bit tricky, because I know my momentum in this case, because they're standing still, my momentum is 0. Right? My momentum's is 0. That means that my net momentum over here also is going to be 0. In order for that, but wait, there's numbers here. How's that going to happen? Just a mental piece to keep to the side, although we can still calculate it. A negative plus its same value positive when added together equals 0. So I know that this is going to be a negative because it's 45 times 3 and it's also to the left, right? So it's negative 45. So I'm going to have negative 45 times 3 plus 1.5 times my second momentum. I'm going to move this over to a sticky note just to make it a little bit easier to figure out. 0 is equal to negative 45 times 3 is, so negative 135 is equal to 1.5 times m2. So, let's go back. We're not looking for a mass. I know that if my momentum is negative 45 in this way, this also has to equal 0. So that's my missing momentum. So I have 0 is equal to negative 45. That's my momentum of object 1. Momentum of object 2, I don't know. So I can go through all the math of plus 45 to both sides. The other thing I can remember is that if they both equal 0, if this is negative 45, then this has to be positive 45. And then I can go back and I can figure out, so I have my mass, I can then also figure out what my velocity was, or how fast this object is going. This question doesn't ask me to.